Hey guys, this is another edition of Biological Basis of Behavior e-tutoring demonstration. Today we are going to be talking about action potentials, which are very, very, very important. You will be talking about these pretty much for the rest of the semester and in any neuroscience course that you take. You will talk about these. So they're quite important. Okay, so first and foremost, you have to understand where action potentials are occurring. They are initiated in the axon hillock, which I will circle for you. The axon hillock is in that area. All it is where the action potential actually starts. Again, well, I never said it, but your action potential only happens in the axon. So, it only occurs here and here. Right? Okay, so your action potential only occurs in there. But more specifically, your action potential is going to occur in the unmyelinated portions. Wow, that was a really good straight line. Anyway, okay, so your action potentials are going to occur specifically in the unmyelinated portions of the axon. So if your neuron is myelinated, because not all neurons are, but if it is, your axon is only going to occur within your action potential is only going to occur within your nodes of Ranvier. Meaning the naked parts, I like to say. So all the parts that don't have myelination is where your action potential is occurring. So the only reason this is true is because in order for an action potential to occur, you need to move around some ions, which we're going to get into next. So you need to move in ions in and out of the axon. You can't do that if you are covered with myelin. Think of, this is kind of a weird analogy, but for some reason it works. Think of when you need to go to the bathroom, you have to take off your clothes so you can go to the bathroom. Think of the myelin as clothes preventing you from going to the bathroom. You need to remove the myelin in order to have the movement of ions. You need to be naked in order for the movement of ions to occur. That's what's important. If you don't have any myelination on neurons, which can happen, then you just have an action potential occurring all up and down that axon. The importance of myelin, though, is that it's going to increase the sorry, I'm sick and I can't think straight. It's going to conduct electricity a lot faster than an axon that does not have myelination. Why? Because your axon is going to... Wait, let me get a new color. Your axon is going to jump to each node. It's called saltatory conduction. That's why it's faster, because you can think of your unmyelinated axon, an action potential occurring there. Think of it as walking versus nodes of Ranvier and myelination. Think of it as jumping, saltatory, jumping. You can get to your destination a lot faster if you jump there versus if you walk there. Just because with each jump you're going farther and farther versus with each step and walking you can only stretch so far. You can only stretch your legs so far, if that helps. So just to recap this slide, action potentials only occur within the axon, which is the dark blue. They are initiated in the axon hillock, which is red. If you have an axon that is myelinated, then the action potential is only going to occur in the node of Van Meer, which is green. If you have an unmyelinated axon, it's just going to go straight up and down. Well, it's going to go straight up the axon. And then specifically for myelinated axons with nodes of Van Meer, you're going to have saltatory conduction, which is purple, and it's going to increase the conductance of your action potential. It's going to increase the speed. Now, let me see how I change the slide. Okay, bear with me, because I'm trying to change the slide, but it won't let me. Okay, I have figured it out. I need it. Okay, doesn't matter. Anyway. So, now I have to regain my thoughts. Oh, okay, so remember how we said that action potentials, in order for them to occur in the axon, you have a movement of ions. This slide is going to talk about the movement of ions. For your exam, the best thing you could do, is I'll draw one too, is make a makeshift, is make your own memory, and then you should draw where your ions are primarily located. Your Na is primarily located on the outside of the cell, as well as your chlorine. The picture on the left also says that, but I'm just drawing it out to help you guys out. On the inside, you're going to have your potassium and your negative anion. So that's the best thing you could do, because then you can understand where your ions are going to flow during an action potential. I'm going to explain the picture, even though it's the same thing. So, on the inside of your cell, you're going to have primarily, the bigger letters are what's primarily located where. But I'll explain. So potassium is primarily located on the inside of the cell, hence why it's bigger. And a negative anion can never leave the inside of the cell, so it's always on the inside. You do have small amounts of sodium and chlorine on the inside, but their concentrations are smaller on the inside than they are on the outside, hence why sodium and chlorine are bigger on in the extracellular fluid. Same idea with potassium. You're going to have small amounts of potassium on the outside of the cell. That's going to make more sense when we talk about sodium-potassium pumps. So in terms of action potentials, these ions are going to move in a certain direction. This graph is very good to understand because it's going to help you give names to the ion movements. So I'm going to flip back and forth between this page and this page. On the last page just is text explaining what I'm saying. So your first step in an action potential, well, the first thing that needs to be done, RMP is your resting membrane potential. This means that your cell is chilling at negative 90 millivolts. I was about to say negative 90 degrees. Negative 90 millivolts. This is, your cell is chilling here, your neuron, meaning there's no action potential happening. When you, say it this way, your threshold level, it's around negative 65, for some professors it's negative 55, it's in that range. Your threshold level is a level that you have to reach in order for an action potential to actually be triggered. So before you can go up here and be depolarized, you must reach this level of millivolts before you can continue the rest of your action potential. So now that that's explained, you've reached your threshold level. Now you want to trigger your action potential. The first step is, I'll go to this slide, Well, A was you reach your threshold level. B, when you reach your threshold level, you're going to open your sodium channels. So now let's think of where sodium is. Sodium is primarily on the outside of the cell. So when you open sodium channels, it's going to go down its concentration gradient, meaning it's going to go from an area where there's a lot of it to an area where there's not a lot of it. That's due to electrostatic pressure. It's a term that you should know, but I'm not going to explain it here because it's important, but it's not that important. So, first step is you're going to depolarize the cell by opening your sodium channels. When you open your sodium channels, your sodium is going to go inside to the intracellular fluid. That's called an influx of sodium. You need that to depolarize your cell. Why? Because depolarization means you're becoming more positive. In order to become more positive, we have to let some positive sodium into the cell. That's the first step for depolarization. Right, so we've reached this level. Opening a voltage-gated sodium channels. Now, that's going to keep happening. I'm going to keep letting in sodium until it becomes so positive. I don't want to be that positive anymore. I want to come back down. In order to come back down, I have to release some of that positivity. So to release some of that positivity, I'm going to open my potassium channels. And since my potassium channels are my potassium is primarily located on the inside, that means it's going to go down its concentration gradient. It's going to flow to the outside of the cell. Potassium is going to flow outside. That's how we're going to repolarize the cell. So I'm going to release some of the positivity by opening the potassium channels. But at the same time, I'm having sodium come in and potassium come out. That's not really relieving the positivity. So to relieve that positivity, I have to close these sodium channels. Once I close these sodium channels and I leave my potassium channels open, I repolarize my cell, meaning I'm going to go back down to the negative state that my cell likes. So that's repolarization. Closing your sodium channels, but you're opening your potassium channels, so that way you can relieve some of the positivity that's inside the cell. So, now my sodium channels are closed, my potassium's open, I'm having constant positivity leave my cell, so that means my inside of my cell is becoming more negative. Then you're going to enter a hyperpolarized state. This is important. Your hyperpolarized state means that your potassium channels are going to stay open for a prolonged period of time. And they're going to become, the inside of your cell is going to become so negative that you hyperpolarize the cell. That means I'm very, very negative. People ask why would the cell do this? It's so that another action potential can't be triggered. It's called, it's part of the absolute refractory period, relative refractory period, and so another action potential can't be triggered. Then, after hyperpolarization, and I've completed what I have to do, I close my potassium channels. Once I close my potassium channels, my cell is going to go back to resting membrane potential, but it's not going to do it by itself. So get this star note thing. Your sodium potassium pump is only active when an action potential is not. Meaning, when the cell is chilling in this RMP, in this resting membrane potential, I gotta keep my potassium primarily inside and my sodium primarily outside. Because if you notice, I have some potassium on the outside, some sodium on the inside. So what's going to happen, I'm going to keep this resting membrane potential, I'm going to push 3 sodium outside of the cell. For every 2 potassium I push back in. Those numbers are always the same. You are going to push 3 sodium ions outside of the cell and 2 potassium inside the cell. 3, I don't want these sodium ions inside my cell, and K is going to come back in. This is important to keep your resting membrane potential because I want sodium primarily on the outside, so that's why I'm pushing 3 sodium out. 3 of these little ones outside. I want potassium primarily on the inside, so I'm going to push 2 of these inside the cell so I can keep my resting membrane potential. Your sodium potassium pump is happening when this is not. So it's like way over here. When you don't have an action potential, your sodium potassium pump is working to keep you at your resting membrane potential at that negative 90 millivolts. That's pretty much it. This is what I described verbally. I wrote it down here for visual learners. So, enjoy.